Thanks, everyone. My name is Admir, and I'm a software architect at Authority Partners, like most of you here probably. Today we'll be discussing how to design and architect. It's not working.
Have you plugged your in?
This is some sabotage right now.
Start risk.
It's very super.
Just start. Do the presentation. I'll fix it.
Again.
No, you just
Okay.
keep talking.
It's completely stuck just the first. Okay, maybe it's not. Okay.
It's your laptop.
So today we'll be discussing how to design it. Okay, I already lost few minutes, precious minutes. Like today we'll be discussing how to design and architect applications powered by large language models. I will be covering a few of the most common, let's say, design or usage patterns that we see in today's LLM applications. Provide some examples, architectural examples, and explain some related concepts along the way. The general idea is to provide an overview of the current state of LLMs and LLM-based applications. But before we dive into these patterns, I will just take a step back and use a few minutes to revisit some foundational concepts related to ideas related to LLMs, which should set the stage and serve as a segue into our discussion today. Large language models, which are the foundation of generative AI, are kind of showing an impressive capability to solve problems that they are not explicitly trained to do. So in some cases, they can do it out of the box. In some other cases, we have to provide a few examples or instructions for the model to learn or to pick up the pattern, basically. When we ask the model to do something that it was not trained to do, we call that zero-shot prompting. And as you can see, it's kind of like a sophisticated term for a very simple concept. Like we generally like to do that in this industry. So zero-shot prompting basically means asking the model to do something without providing any examples on how that task should be solved. And if you ever use ChatGPT, chances are that you've used it in a zero-shot setting, right? Zero here means basically that you are providing no examples to the model on how a particular task should be solved. You just ask the LLM to do it, and then it generates the answer based on its own understanding of the natural language and based on its own, based on the information that it learned during the training, basically. This zero-shot prompting can be useful, of course, but it's mostly useful for some simpler problems, exploratory queries, and problems that can be solved with only using general knowledge. It does work well for more complex problems, for problems that require some additional data, and especially when a very precise output format is required. And that's basically most of the times when building LLM applications, because most of the times you want to be able to read what the LLM returned so that you can pass it to some downstream processor application. Now, similarly to zero-shot prompting, we have few-shot prompting. Few-shot prompting means asking an LLM to do something while simultaneously providing, I hope these examples are kind of self-explanatory, asking an LLM to do something while simultaneously providing examples on how that particular task should be solved. It is useful when we want an LLM to learn some new concept or when a very precise output format is required. It is basically like passing a small sample of training data to the model in our query, in our prompt, so that the model can learn from these user-provided examples. Now, zero-shot prompting is enabled by the capability of LLMs to learn from the data provided within the context. That's the wider concept, and it is known under the name, it's an obvious name, in-context learning. And much of the today's interest, actually all of the today's interest in LLM is almost due to this. And most of the applications that we build, LLM-based applications today, are in some way probably, there are applications that use fine-tuned models, stuff like that, but most of the stuff that you see being built today is actually based or in some way leveraging the in-context learning capability of LLMs. To illustrate, in-context learning is not limited only to few-shot prompting. Few-shot prompting is just like a manifestation of in-context learning, like a way to utilize that capability. But we don't always want to provide examples, right, on how a task should be solved, like those input-output pairs that the model needs to mimic, sometimes simply including some additional data in the context can help the model provide more accurate answer without actually providing those input-output pairs that the model needs to make. Like, to illustrate, imagine asking your friend like to solve a math problem that you don't know how to solve, but you have a math book, and then you give them that math book at the same time, right? You ask them to solve the problem while simultaneously providing them with the math book to use as a reference, basically. So you are at the same time telling the model how to act, what to do, and providing the information that the model needs to know, but it doesn't know, out of the box. But that's generally like in context learning. In context learning is especially useful if we want to work with the current data, like more recent data, or private proprietary data. In fact, connecting your private data in some way, integrating your private data with an LLM can unlock much more valuable opportunities and use cases than simply using LLM in that zero-shot setting that we discussed before. I wanted to start with this introduction because in context learning is I said earlier, it's kind of the reason for this whole interest, in LLMs probably, and it's kind of easy to do, right? It's not an AI. Generally, you're not training your own model. You're just, providing some instructions, to the LLM through the prompt. It's not really machine learning in a way that we were used to it, before LLMs. And everything that we will be discussing today is actually based on in-context learning. So let's start with the first design pattern, or maybe it's better to call it usage pattern because there isn't really a lot to design here. As you can see on this illustration, it was intentional, like simple. The first design pattern involves only using large language models. It sets itself apart from other kind of usage patterns in that it doesn't involve direct interaction between the user and an LLM. Typical use cases include leveraging large language models for some very specific and narrow tasks, such as, whatever you can come up with. For example, translation, summarization, information extraction, anti-instruction, semantic analysis, even image classification with these image models, and many other forms of reasoning, basically. And in all these scenarios, LLM is actually involved programmatically through your code rather than by an end user through a chat interface. And as you can see here, like this simplistic approach simplifies many aspects of developing LLM applications. There isn't, as I said earlier, there isn't a lot to design here from the architectural perspective. There is, of course, your application, but that's not the focus of our discussion today, right? It can be more or less complex, but from LLM perspective, they're just an LLM API call, right? Nothing else. So, this kind of approach, I like it because I think it's very applicable to kind of existing projects. And with all this hype and interest, hype around chatbots, assistants, co-pilots, agents, and whatnot, I feel like this usage pattern has been kind of overlooked and a little bit underappreciated, right? While I believe that this is actually one of the greater values of LLMs, the fact that we can now use that, let's say, universal model, right, to solve tasks that would previously require, right, dedicated teams of, data scientists, machine learning engineers, and a lot of time for collecting data, cleaning data, training the model, and whatnot. And now you can, it can be done by one single person or much smaller team by using an LLM. So, while again, there isn't a lot to design here, I prepared a couple of examples just to give you an idea of what you can actually do with just calling an LLM. Without, not everything needs to be chat application, right? We can use LLMs in any other way. So the first example related to this first design pattern is semantic analysis. This is like a mainstream example, probably. What we have here is, we are leveraging an LLM to determine the sentiment of messages within an event stream, following standard architecture best practices for building any event stream application. Again, that is not the focus of our discussion, right? And then we have an LLM running in a separate service, hopefully. It should run in a separate service, either as a managed service, right? Most often that way, right? You are using someone else's API, like OpenAI API, basically, that runs closed proprietary models such as OpenAI GPT models. Or it can be obviously some self-hosted service which runs some open source models such as Llama, for example. But in any case, it should be definitely, like if there is anything like to take away from this, again, is it should be hosted as a separate service. Don't ever run it. I guess it's a common sense, but just to mention it again, don't ever run the LLM in the same like process as your application. It's just different kind of type of workload. It has different life cycle. Probably you will be deploying your application much more often than the LLM. It has lower startup time because it has the download weights. It probably requires some specialized hardware such as GPUs and stuff like that. So always a separate service. But you'll if you are just starting, you'll probably be using OpenAI API. So that problem is resolved. So at some point, a function within the stream processor just makes an API call to the LLM, instructing it to perform a specific task, in this case, to determine the sentiment of the messages within an event stream. This whole interaction between LLM and our application is completely text-based. So in addition to LLM, we generally need to have a prompt template where we actually provide some of our instructions. And in addition to that, we describe the desired output to LLM. And then also we have to build the output parser, obviously, that will be able to interpret that result and kind of convert it into a structure or some structured format that can be passed to the downstream processor or application. And then, obviously, this is just one example. Maybe sentiment analysis is not even that great example because it was solved even before LLMs, right? But you can come up with something else. I don't know. I remember like a few years ago, we had an internal discussion about I'm not sure if it was a project or a potential project, but it was about analyzing articles to determine the media political bias, basically. Are they more left or more right? Like back then, like a few years ago, that probably required like a lot of data, right? Training everything yourself. But right now, I believe it can be solved with a prompt and LLM. You stick your whole the article in the prompt, send it to LLM, will probably give you fairly accurate results. So you can do basically many forms of reasoning. Let me also give you an example of a promising experiment that I was working on. It was experiment, not completed, but I think it is kind of worth sharing because it's an interesting, at least for me, use case for this first usage pattern. I was exploring kind of how to leverage LLMs to help us review test cases, and not just to help us, but actually to do it for us. And what you see here is a diagram or some kind of a functional architecture diagram, right? That shows a very specific implementation of this use case where we are the specific use case that uses pull requests as a mechanism to trigger test case review process, and then application that is triggered, that works that runs in the background. It uses an Azure DevOps API to read acceptance criteria of the work item linked to that pull request, and also title and steps of the test cases associated with that work item. So it first pulls the data, and then the test case review process is executed in 2 steps, both leveraging LLM. Again, just API call, right? No chats, no agents, nothing in this case. We are just kind of calling an LLM with very specific instruction. In the first step, LLM breaks down the acceptance criteria into, let's say, standalone, like isolated business requirements. And that step is meant to normalize the requirements in order to accommodate like different writing styles, basically. So it kind of converts one acceptance criteria, one text into a list of business requirements. And then in a second step, the application iterates through all test cases, calling an LLM, instructing it to identify which of these business requirements, which it kind of isolated in the previous step, are covered with that specific test case. And then after we iterate through everything, at the end, we can easily pinpoint any requirements that are not actually covered with any of our test cases. And then we can generate a report highlighting these gaps and then post it as a PR comment, for example, for someone to review. And it doesn't even have to run like this, triggered by PR. It can be run on a demand, like with the click of a button, or even by a person writing these test cases as a form of a self-check. And there is a third example. Again, we are still in that first usage pattern. We're just calling, one single API call almost, right, to LLM, very simple to implement. This is called like a smart paste. You can think of it as intelligent, like this is not like complete application based on LLM. It's just like LLM enhanced, right? A small feature inside an existing app that is based on LLMs. You can think of it as a kind of intelligent application feature that uses an LLM to, to automatically fill any form inside your application. You can technically use it in any form, but just to give you some idea, and you have this animation here, a user could, for example, copy the whole address from an email or a Word document, then go in the application, and then just use smart paste feature, and behind the scenes, LLM would extract relevant information and automatically pre-fill the whole form. Or even something interesting for our kind of for our domain, for our work. Imagine like someone reporting a bug, to you, sending a short natural language description of the issue on Teams, email, right? And then you just take that, whole natural language description, you go to Azure DevOps, create new bug, and you use smart paste feature, and it automatically pre-fills the title, severity, and even repro steps, for example. LLM can rephrase like the original input from something like, hey, I clicked on this button on this page, something bad happened, to, repro steps format. Navigate to this page, click this button, right? So it could automate, our work. So all these three examples were very simple. Again, this first design pattern, there is no chat involved, nothing. We are just using an LLM to make a single API call to perform a specific task. The idea was just to, at least try to inspire some ideas, for you on how you can leverage the LLM on your own projects. As shown with just, a little bit of prompting, like prompt engineering, and by leveraging in-context learning, we can solve like various tasks that would have previously required dedicated teams and a lot of time probably. And I'm sure that this whole excitement about chatbots and agents will eventually wane. But as a computational tool, LLMs are here to stay probably, right? So for me, these kind of simple cases are, what makes a difference right now. That was it for the first design pattern. The next design pattern involves both large language models and design pattern or usage pattern. I call it design pattern here. Maybe it was better to call it usage pattern, really. Involves both LLMs and data, or integrating our private data with LLMs. Typical use cases include, this is actually a usage pattern that you see in most developers and companies actually start with. And typical use cases include question answering, information retrieval, chatbots or conversational agents, and so on. And the core idea of RAG is actually to ground the model responses in some source of truth by providing some external information that the model was not trained on. For example, I still need to stay on this one. For example, let's say you're building chatbot that can answer a set of your documents. For example, user support agent that can answer questions about your documentation. Taking a very naive and simple approach, that's what you see here. We can just take the whole of our documentation, all of the documents, copy to ChatGPT or GPT-4 prompt, and then start asking questions at the end, right? And that could even work for very small data sets, like a few pages, maybe even that is, okay, but it doesn't scale. The latest OpenAI GPT model, GPT-4 Turbo and GPT-4 all have 128K context window sizes, which means that they can process about 200 pages of text, which is a lot, right? And it's constantly increasing. However, as we approach that limit, performance degrades badly. And by performance, we mean both inference time, cost, and accuracy or output quality. I think Admir mentioned earlier that as you kind of add a lot to the context, some stuff gets lost. There is this kind of phenomenon that these researchers, call lost in the middle. So if you have very long context window, LLM tends to focus more on the content in the beginning and end than that content in the middle for very large context window. So it's not just feasible, And on top of that, filling such large context window, like 128K tokens for each request, would be cost prohibitive for most applications. And then the reg actually solves that with the, let's go trick by, instead of sending all the documents with each prompt, with each query, we actually send only a handful, only a few of the most relevant documents. And the most relevant documents are actually determined with the help of, again, LLMs, right? Not exactly LLMs, but by the embedding models, which are kind of correlated, related, usually, a byproduct of LLMs as well. So how does that whole process work? The whole workflow can be broken down into 3 stages. That is embedding, retrieval, and generation. Embedding stage involves moving our unstructured data into, to be retrieved later. It usually involves like breaking down the documents into pieces, into chunks, passing them through an embedding model, and then storing them in a vector database. Retrieval basically involves searching now that vector database for the relevant content. And then I'm speeding up a little bit this part because we will get back to it later on. And then the generation part actually involves taking that retrieved content, kind of adding it, combining everything into one prompt, calling an LLM with that prompt, and then LLM generates an answer. Now, if you never build anything like this, it might seem like a lot of steps. However, it's much easier than the alternative. LLMs currently have 3 ways to learn, right? There's either training LLM from scratch, like your own LLM, probably not an option. Fine-tuning an LLM, then the second way, how they learn, and it's okay, for some tasks. And the third way is in context learning, basically, which is the easiest of the 3. And it basically reduces an AI problem to the data engineering problem, which most of the companies already know how to solve. It's kind of, search problem, essentially, in the end. And on top of that, the in-context learning even tends to outperform fine-tuning in a lot of cases. For example, if you want to learn a model new facts, right, then in-context learning is much better than fine-tuning. Fine-tuning is more appropriate if you want the model to learn a pattern. If you want the model to learn facts, like such as your documents, right, then in-context learning is a better option. And on top of that, it can actually incorporate new data, like new changes in real time, which fine-tuning obviously cannot. You have to retrain your own model. I mentioned already embeddings a couple of times. So what are embeddings? Embeddings are basically way of representing words or other data as vectors in a high-dimensional space. You will probably remember vector from a math class as an arrow pointing from one point to another, right, on a 2-dimensional or even 3-dimensional graph. It really is just a point or some data in space, right, or dimension. And high-dimensional in this case means that we have many dimensions, a lot more than we can actually see or imagine, like hundreds of dimensions, right? We are used to see the world in 3 dimensions. We can also, see and imagine 2 dimensions, but not more than 3, right? The idea is that similar vectors will have similar words or other data. Like it doesn't always have to be text, but forgive me if I forget sometimes to mention or other data. So the idea is that similar words or other data will have similar vectors, and different words or different data will have different vectors, and then we can use this actually to determine how related or unrelated they are. So embeddings are very important because they can capture context and meaning of words or other data in a way that computers can actually understand and process. But how do they really work? So let's see that as well. So consider these 4 words: man, woman, boy, and girl. 2 of them refer to males, and 2 of them refer to females. 2 of them refer to adults, and 2 of them refer to children, right? And then we can also plot these words in a 2-dimensional graph as points to a 2-dimensional graph, where x-axis represents gender and y-axis represents age. Right? I hope this is relatively clear. So gender and age are in this case called semantic features because they represent part of the meaning of each word. And if we then assign the numerical scale for each of these features, we can then, if we associate numerical scale, we can then assign coordinates to each word, and then we can plot them on this 2-dimensional graph. But now consider adding additional words like king, queen, prince, and princess. Like these 4 words have the same semantic features, like the same gender and age attributes as man, woman, boy, and girl, right? But they don't mean the same thing. In order to differentiate man from king, woman from queen, and so on, we have to create some new to add some new semantic feature in which they differ. And in this case, we can call it royalty, right? And we add another dimension, but now we have 3 dimensions. We cannot anymore, represent our space in 2 dimensions. We need 3 dimensions to kind of plot these points, because each word now has 3 coordinates basically: gender, age, and royalty. And these arrays of numbers are basically called vectors. And since they represent the values of semantic features, we can also call them feature vectors. And what can we do with this? Already mentioned before, we can actually use these numbers or these vectors to actually determine the similarity, to figure out how similar the words are. And the general idea is this: the boy is more kind of similar to girl than to queen, because the distance between boy and girl is smaller than the distance between boy and queen. That's the general principle. There are many different ways how to calculate this distance. We won't go into details. But what you need to remember is that semantic distance is basically a way of a measure of relatedness of words. Okay, now going up from these 2 to 3 dimensions allowed us to represent more words. Our vocabulary increased, right, from 4 to 8 words. However, is that enough? Probably not, right? How could we represent words such as, I don't know, cucumber or smile or computer, architect, summit? We cannot represent any of these words with the semantic features, gender, age, and royalty. It doesn't make sense, right? So probably going up to 4-dimensional, 5-dimensional, or 6-dimensional space would allow us to represent more words, but that still won't be enough. Okay, we would be able to represent more than 8, but to represent the complexity of the typical 50K words English vocabulary requires hundreds of features. And what you can see here in this image is actually an embeddings for 6 words. You can see them here that are represented with 300-dimensional embeddings. That basically means that each word is represented with 300. Like you remember, we had gender, age, and royalty. Now we have 300 numbers with values between -0.2 and 0.2. Now, designing this rich semantic space and so many features by hand, and then assigning correct, accurate coordinates to each one, correct values. Each line here is basically one number. This is just another way to visualize. Remember, we cannot really now anymore draw it as graphs. So this is just a way to visualize embeddings. And designing this by hand and then assigning correct coordinates would be almost impossible, probably, or require a lot of work. And we don't actually do it manually. So we can actually use computer to do that for us, to create a semantic feature space for us by supplying a machine learning algorithm with large, huge amounts of textual data, so that it can actually discover statistical relationships between words by looking at which other words they co-occur with. I mean, there's simplification of it, but that's generally what it does. And then it uses that information to create a semantic feature space of its own design, and then create these word embeddings. So when we say semantic feature space of its own design, that means that we have no idea what this means, right? It doesn't mean anything to us. Previously, we were designing semantic feature space. We know the first number is gender, the second is age, the third is royalty. Here, we let the machine learning model actually create semantic feature space, of its own design. ML model knows, it means something to it. It doesn't mean anything to us, but we don't care, right? We can still use it to actually capture the meaning and context of the text. So we don't actually calculate these embeddings or generate embeddings by hand. We actually use an embedding model for that. And for that purpose, most of the people are currently using OpenAI API. Just like they have an LLM model, they have an embedding model as well. It's easy to use. I don't know, it gives reasonably good results. It's becoming increasingly cheap. The latest OpenAI embedding model, text embedding 3 large, can actually create embeddings of up to 3072 dimensions. We had 300 on the previous image. This one can create 3072 dimensions and costs 13 cents for 1 million tokens, which is very cheap, especially considering the fact that you don't generally index data multiple times. You index it once, and then again, if it changes, right? So unless you have some very specific requirement like security or privacy concerns, or you're looking for some very specialized model, there's really no reason to not to use OpenAI in this case. There's one thing I would like to mention, might be important. You're all architects here. Is the dimensionality. Dimensionality generally, the more dimensions you have, generally you will get better performance, accuracy, given the same. Obviously, the quality of the model is the most important here, but given the same model, generally more dimensions will give you better accuracy. However, this will have direct impact on your vector database. It doesn't maybe sound like a lot, but for a little bit larger project, you can count on having millions of embeddings. And then, if every embedding needs to be represented with 3072 numbers, that really increases the requirements for the storage space, for the memory. They can really impact your kind of infrastructure choices, basically. I'm not saying, that you shouldn't go with the highest embeddings, but just, make your own judgment because it comes with a price, right? Sometimes going from 512 to 3072 can bring 1%, maybe accuracy improvement. So just do your own, weighting, basically. Is it worth? So I already mentioned vector databases. The most important part of the data ingestion pipeline is arguably, at least from this system's standpoint, architectural standpoint, is probably vector database. Vector database is the specialized type of the database which is designed to insert, index, and query high-dimensional vector data. So basically what I just described before, right? So embeddings, essentially. There are many types of vector databases available today. The most common choice we've seen is Pinecone, probably because it was the first fully cloud-hosted, so it was the easiest to use, right? You would just call an API and you're done. Followed by these open-source vector databases such as Quadrant, Chroma, Milvus, and so on. And all of these open-source versions these days offer their own kind of cloud service, basically, so you don't need to host them yourself either. Now, in your work, you'll probably stumble on local vector libraries such as Space or HNSVlib. These are great for experimentation, for smaller projects, POCs. However, they are not, it should not be a replacement for a dedicated vector database when operating at scale. And additionally, vector support is today available in many traditional like databases, SQL, NoSQL, such as Postgres, Cosmos, Redis, Cassandra, and so Mongo, and so on, as well as in the text search engines such as Elasticsearch. So if you're already using some of these databases, like traditional one, and you need vector support, this is probably a good solution. You can certainly consider it. Although I'm not sure in the long run if it's how feasible and would it be recommended to actually tightly couple these vector and scalar workloads, right? For some smaller projects, again, you probably can get away with it, but for bigger projects, make your own judgment. Both approaches have their own pros and cons, but it's good to know that these traditional databases now come with vector support as well. And now going back to that design pattern, you remember the RAG design pattern, integrating our own private data with LLMs. Previously, we've seen a very simple, naive approach, right? We take all the documents with every single input, send everything, ask an LLM question about it. We said it's not scalable. What you can see here now is an improved, enhanced architecture, which kind of integrates everything that we talked about so far. The architecture consists of two main kind of components. One is data ingestion pipeline. The second one is the RAG chain. Data ingestion pipeline is basically involves moving unstructured data, documents in our case, on the left side to the vector database on the right side. But in order to do that, we have to go through a couple of steps. So the first step, obviously, is the extraction. So if we have a bunch of documents, right, we first need to extract the content, the information from those documents. This can be very simple using many libraries, right? You just get the content of the document and that's it. However, it can also get very complex depending on your use case and depending on your documents. For example, you might need to ensure that images, tables, graphs, math formulas, like everything that can be in the documents are actually extracted in a meaningful way, especially if it contains very important information that you obviously have to index. Again, it depends on your scenario, but can get quite complex, this whole step. For example, you might have a bunch of PDF that are scanned, there is no any text there, so you have to do OCR. So can be very simple or but can get very complex as well. The next step after you extract all of the content, the next step is called chunking. Chunking involves breaking down that whole that document. Basically, let's go. We are now iterating through each document, right? Breaking down the content of one document into multiple pieces, into multiple chunks, and this can be done again in many different ways. The simple way would be probably on sentence boundaries. So you kind of split it by sentences. The second one would be maybe by fixed count of words, tokens, characters, or something like that. Or any other techniques, such as maybe using an LLM to break down this whole chunk into atomic proportions, for example. So again, can be either simple, can get more complex. The most simplest one is probably just deciding on the length, the size of the chunk. Let's say 500 characters, and then that's your kind of chunk. And then in order to preserve the context, you also include some overlap there, so that you don't cut in the middle of sentence. So every chunk kind of overlaps with the previous and the next one. Let's say with 100 characters. That is the most simple chunking strategy. But the point is that the whole content of the document is broken down into multiple pieces. And then the next step, I didn't draw it here because it's kind of part of the chunking, is metadata extraction. Metadata extraction basically means assigning or augmenting these chunks with some additional metadata, which can really be anything. Most often it is like the ID of the document that the chunk came from. It can be the number of the page, some nearby or other related chunks, and pretty much anything that can help you later in the retrieval stage to retrieve more accurate content. For example, I'll give an example from our API assistant. I'm not sure if that was implemented. I know there was like some talk about implementing it, but just to give you an idea what metadata can be used for, we have that API assistant that answers questions about policies, and we have some policies that are different for Bosnian consultants, Turkey consultants, Dominican Republic. Usually those policies that are kind of dependent on the local laws. So it's the same thing, just same title, same purpose of the document that applies to different people. You could technically store that in the metadata. So when I ask the question, the LLM doesn't get confused and give me an answer that is supposed to be for Turkey consultant or someone else. So metadata, basically any kind of property that you can assign to your chunk that can help you later on in the retrieval stage. And then the final stage, the embedding stage, obviously. All of these chunks need to be embedded. We need to generate the embedding for each of them. And this basically involves passing them to an embedding model, which is generally just an API call. Now, in the simplest form, embedding is generated for each chunk. So remember earlier we said, words. Sorry, I forgot to mention that previously. We were explaining what are embeddings. They are kind of represent the meaning of words. It doesn't have to be just words. Obviously the basic block is the word, but it can capture the meaning of the whole sentence or the paragraph and so on. So usually we embed the whole paragraph, the whole chunk, basically, to broke it down. So in the simplest form, we generate an embedding for the whole chunk. In the more complex and let's say sophisticated data ingestion pipelines, we can actually ask an LLM which questions does this chunk answer, or which topics does this chunk cover, right? And then instead of embedding that original, that source text of the document, basically, we actually create embeddings for those, let's say, hypothetical questions that LLM provided, because they are more likely to be aligned with what the user has. So there are, the point is that almost each of these steps, can be very simple, but it can get kind of quite complex depending on your needs. But it generally can be broken down in these steps. And then in the end, after you generate these embeddings, that obviously needs to be stored somewhere. We use vector databases for that. And usually, together with the chunk, like with that vector and that metadata, we usually also store the source content, with that chunk content, essentially, that we kind of generate an embedding. And it's typically just a property, one property in the method. And that is our data ingestion pipeline. This obviously runs asynchronously. It's not part of our main application runs on the side. Just think of it as indexing. It's just a different type of indexing. And then the second component is the reg chain. That is actually our application. This is usually the backend of our application, right? We have some kind of generally chat-like interface, and for each user query, for each user input, the first thing that needs to be done is that we need to generate embedding vector, right? Again, for that user input. And it has to be, the same embedding model that we use, obviously, to index the data. Because, in order to find the relevant content that is relevant to this input query, we need its vector, we need its embedding, so that we can search the vector database, right, with that vector, essentially, to find the most other vectors that are close, essentially, to that one, which means that they are kind of relevant or similar to that one.
Embedding is basically the map of the meaning.
Exactly. So embedding vector captures the meaning and context of the data. And then the second step is the retrieval, right? That embedding that we generated on the fly. So this is in the runtime, basically. This is not some side process, it's data ingestion pipeline. We basically retrieve the data from our vector database, and then we just put all of that, like that retrieved content, the user query, like everything, we put everything in one single prompt. Usually, at the top we put context with some instruction. At the end, we put user input query, and then LLM, can generate answer, using that kind of retrieve document. And that is generally, so this whole reg chain is kind of hard coded, let's put it that way, to always do exactly the same thing. For every user input, you will always see the same sequence of steps. Retrieve the information, retrieve the documents, retrieve the relevant information, call the LLM, retrieve relevant information, call it. It's very limited. So this was the second usage pattern or design pattern. And the third one is this is actually the AI agent pattern we had previous presentations. So there's a little bit of overlap. I don't have any demo. I'll go mostly through the theoretical stuff, but it's kind of the similar concept. AI agent pattern, it is probably the most hyped like LLM usage pattern out there. Typical use cases, like this example here, builds on top of our previous example, right? So previously we had like a simple chatbot, right? Like a user support agent that can answer questions from our documents. This is like an upgraded, like let's say more advanced agent that can, that builds on top of our previous example. So as you can already imagine, typical use cases for agent include more advanced, at least right now, more advanced chatbots and conversational agents, right? For the agent pattern, I mean. If you anticipate user questions triggering multiple rounds, for example, of knowledge retrieval on different topics, or being able to invoke external APIs and being able to act, like to take action on behalf of the user, then the agent kind of workflow is probably the way to go. If it's more simple, you just need to answer questions from the document, and the reg is likely going to be sufficient. So AI agents kind of give applications new set of capabilities to solve more complex problems. Most importantly, to act on the outside world, and even to kind of learn from their own experience post deployment. We will get to that in a couple of minutes. So, as you can see on this diagram, there are some kind of similar things. We can still see data ingestion pipeline. It still exists. We don't want to remove that capability, right? We still want our user support agent to be able to answer questions about our documents. So data ingestion pipeline is exactly the same as it was in the previous example. No need to cover that. But the differences lie in how this architecture actually uses the LLM and how this retrieval is actually, that information retrieval is integrated into the workflow. Basically, you can see that, remember in the previous example, the whole reg chain was kind of hard-coded, right? To always do exactly the same sequence of steps. For every user query, you retrieve the relevant documents, you call an LLM. Retrieve relevant documents, call an LLM. And exactly, every query is the same. That it's very linear kind of architecture. In this case, this architecture, this kind of example builds an architecture, an agent, sorry, and for each user query, agent first uses an LLM. So that's the first difference, right? We don't retrieve any information here. Agent first uses an LLM to reason about the question and figure out whether the question can be answered or some action needs to be taken. And we say action, it can be pretty much anything, basically, like you saw in the previous example, various kind of tools. In our case, we have two tools here. One is called retriever. This is basically our reg chain. It's just now exposed as a tool. It's not anymore hard coded in the architecture. It just exposed as a tool. So when agent decides that it needs to retrieve information, it will retrieve it. It's not a kind of step before even calling an LLM. We let the agent decide when the tool call is needed. So tools can actually be used to retrieve information, like the reg tool, or they can be used to take an action or to have a side effect on the system outside the LLM application. In this case, we have a password reset tool. It is just an example. It can be anything. So it's a user support agent, right? So a user can come and ask, I forgot my password. Can you help me restart it? And then the agent can use that password reset tool to actually do it on behalf of the user. Those in the previous example, that those fixed chains, like predetermined chains, they are useful when you know exact sequence of steps that needs to be taken for every user input. However, that is often not possible. And in those cases, it is better to let the LLM kind of decide which tools to use, how many times to use them, in which order, and so on. And I think this is like common sense, but again, there are some people who are not technical. Just to reiterate, while LLM can decide, what tool to use, it obviously cannot do anything on its own. Right? I guess that's pretty much clear. It's just a language model, and all our interaction with the language model is a text-based. Right? So you send some textual input, you get textual output. It's not like LLM is calling these tools. We have to facilitate that whole kind of agent workflow, by writing the code that can execute the tool and return the tool output back to LLM so that LLM can reason, and decide the next step. But besides that, that's pretty much it, right? That's the architecture there. This is basically our agent. Everything else are tools. So it's very modular architecture, technically. And to implement this logic, this orchestration, you can do it from scratch. It's not even any more hard, especially with OpenAI API and function calling and everything. A lot of these tasks that previously you would have to do manually, are now handled for you. Or you could use LLM orchestration framework. Previous Admir mentioned previously LangChain, and they built their demo in the LangChain. LangChain is one of the more popular LLM orchestration frameworks. However, it's based on Python. It's written for Python. I guess not many here like it. And another option is semantic kernel. That is actually Microsoft product. It is similar to LangChain, the same purpose. And these frameworks typically, generally, right, they abstract a lot of details, of building LLM applications, including prompt management, searching vector databases, connecting with various vector databases, determining when the tool needs to be called, when the LLM said that the tool needs to be called, involving these external APIs or tools, returning back the response back to LLM, basically implementing this loop and also maintaining the memory across multiple LLM calls. So a lot of this stuff is hidden from you, and it's much easier to get started if if it's your first application. But even if you start from scratch, it's not that hard generally. This whole part here, it's harder to implement probably the reg chain than the generic agent architecture. Generic architecture. But then everything else is exposed through the tools. So in addition to this, like using one of these orchestration frameworks will probably give you guardrails for how you structure the application. So it's beneficial to use them. And they come with a lot of examples and a lot of pre-built functionalities and utilities that you can actually use to kickstart a project, and it might even reduce the amount of maintenance required in the future. The tools can really be anything, and you saw it previously. You can think of tools as functions. Literally, if we are using technical language, it's just a function with some annotations, let's say. Annotations being natural language description generally, right? because LLM needs that natural language description to kind of figure out when that function needs to be called. But under the hood is just a function, and more simpler tools can be implemented directly in that function, like that get date tool that Admir showed before. And more complex tools in general are usually part of some external service, which are exposed, through some API, and then you can use open API spec, or you can just use inside your function. You can use, you can make some kind of a proxy tool basically that just calls that other service. Various types of tools, but generally, we split them into, knowledge retrieval tools, and they can be anything. Again, here we are using the reg tool, the same one that searches the vector database from the previous example. It doesn't have to be a vector database always. A tool can expose even SQL database, right? Although, I don't know how much would that be recommended? Probably yes, in some read-only scenario. I personally wouldn't ever, allow it to with the right permissions on the database. But there are tools like text to SQL tool that can generate the SQL query from the natural language input and then execute that query to retrieve data from the actual SQL database. Or it can also be, just an API endpoint like we showed before. Or a tool can actually take an action and have effect on the system outside. It's not just reading the data, right? It's making some changes in the system outside the LLM application by calling an API, for example, or something like that. In this example here, we have the REST tool, so an agent could kind of assist the user, in resetting his password when the user requests that. Exposing this type of functionality is not just this, but anything that affects the external systems can be risky and sensitive. So, a special care should be taken in this case. And generally, there's one thing about the security with these, especially with tools and everything, is that and the instructions that you give to LLM is that you should treat LLM as like a client application, like you treat client application, and any instructions that you give it, in the prompt can kind of be, let's say, jailbroken, right? User can get around that in many different creative ways. So you shouldn't trust those prompts, essentially. If you tell agent, don't do this, don't do that, right? You should not rely on that. You still need validations on the backend. It's the same way, when you're building like client application, in the same thing. You have validations, right, on the client side just to make the user experience better, but you don't rely on those client side validations. You still need validations on the backend side. So it's the same, with these tools and everything. Don't rely on the prompt instructions. It must have a backend validation still. And one more thing I want to mention about the tools. Tools can also use LLMs, right? Our agent doesn't care what is the tool. Again, it's just some kind of abstraction for it, just some kind of a function. So tool can basically use an LLM as well. And it doesn't even have to be the same LLM as the kind of main agent is using. Generally, the main agent needs it needs an LLM for high-level reasoning and planning, right? So it usually needs the most capable LLM, which is usually the largest and which is usually the most expensive. Tools generally need to do very specific tasks. I don't know, for example, our reg tool, the retriever tool, which retrieves information, can use an LLM to summarize information before even returning it to the agent in order to reduce the token usage. And for that, you can probably use GPT 3.5 Turbo. You don't need GPT 4, right, for summarization. Or, I don't know, I mentioned earlier, text to SQL tool also uses an LLM to generate a SQL query from the natural language input. So these tools generally can use LLMs, and it's very often, using some specialized smaller models is much more appropriate than using like a larger LLM that the high level agent. And there is one more topic. It's the memory. By default, LLMs are stateless, which means that every input is considered independently of each other, right? Without considering past user interactions. So when we refer to memory, we are not referring to the inherent capabilities of LLMs, but to the feature of the agent or application that is built on top of LLM. So LLMs don't have memory agents, which is kind of an application basically built on top of LLM, can't have memory. So memory is basically capability of the agent to retain and utilize information from the past user interactions in order to inform and even improve future responses. So it basically enables the agent to maintain a coherent conversation. Now, you can check this example on the right. Notice the second question. What about tomorrow? It doesn't say anything about, what you're looking for, which is temperature, or where, which is Sarajevo, but only, tomorrow, like only when, basically. And without considering the first question, the second question makes no sense. So in order for LLM to understand the second question, it also must be aware of the previous question as well, right? Now, given that they are stateless, they don't, remember anything. The only way to inform LLM about the previous conversation is basically to include the whole conversation history in the prompt together with our last question, and send it to the LLM like that. And that is basically like a memory management in its simplest form. We retain all the messages, all the conversation entries, much like we would do in any chat application. There is some database, some persistence involved there, right? Whatever you prefer, SQL, no SQL, doesn't matter, right? You save all the messages, and not just messages. You also need to store, let's say, invisible conversation entries, because every agent needs, usually until it answers your question, it goes through a couple of steps that the user doesn't see. They're not part really of the chat, but in order to produce that final response, it might call one tool, call another tool, get result from this tool, So you generally store all of that, as conversation entries. Some of them are visible, some of them are not visible basically on the interface, but generally everything is stored in some kind of a database. And then for each agent invocation, for each user query, we first retrieve the chat history, and then we basically put everything in a prompt and send everything to the agent, usually by pre-pending that conversation history, to the last question. So we kind of add it right before the last question. Last question goes, at the end to appear as a coherent conversation. However, this approach comes with a few problems. First, as we mentioned earlier, that the context window is limited, right? So memory is immediately limited by the context window. And also context pollution might be a problem. Like mentioned again previously, if you keep adding, content to your context window, the LLM performance starts to drop, right? The output quality of LLM will probably drop. And also it is not possible, there is no ability to kind of synthesize deeper insights from these raw messages, raw observations. So LLMs generally agents need to generally utilize this context window carefully, in order to enhance performance. And there is one very simple solution to that. That is basically to cut old messages. Right? So you just start cutting at some point. You don't send the old messages anymore, and you just load the most recent messages, whatever n is for you, right? For your application, it can be 10, 20, last 50, 100 messages. But at some point, you cut it, which means that LLM technically forgets everything. You still see it maybe in your chat because it's still stored in this database, right? But LLM doesn't know anything about that because you are not sending it with your prompt, right? So you basically cut your messages. And for for many applications, this might be, okay. Maybe you don't need, that very old data, old messages, and that's, this is where you kind of stop. However, if required, this can also be mitigated. This information loss can be mitigated by splitting or partitioning memory into two parts. And we call that short-term memory and long-term memory, much like computers are basically managing their memory, right? When we say short-term memory, that's generally the conversation history. I was already referring to this as conversation history, right? Short-term memory is usually there to help the agent maintain a coherent conversation, to have a dialogue with you. So only the most recent conversation history goes to, let's say, it's short-term memory. So that's all messages that you don't cut off. So everything that you cut off, an LLM forgets technically. However, what we now have long-term memory as well. It is that same vector database I had to cut. I couldn't fit the whole diagram here, but it can be the same vector database that you use to index your kind of documents, just a different collection, obviously. So there is some process very often in this application that moves data from short-term memory, from the conversation, from these raw messages into long-term memory, right? But usually, like this is the simplest, again, approach, usually by synthesizing or summarizing pieces of that very old conversation, right? So we summarize a couple of, let's say, 20 messages, trying to kind of capture the core points of that conversation. We summarize it, we generate an embedding again very similar to what we did with our documents, right? We generate an embedding for that chunk, for that kind of summary, and we store it in the database. And then in the same way, like how we were how we do the retrieval in the red chain, right? How we retrieve our most relevant documents. In the same way, we can retrieve most relevant memories. That's it for me. Thank you.